Okay, so here we are asked to solve for Vx and find the power delivered and absorbed for these sources. So first we're gonna focus on finding Vx here, because once we find Vx, we'll have most of the information that we need to find for these values regardless. So when it comes to these kinds of problems, right, we're told to only use KVL, KCL, and Ohm's law, specifically not node voltage method, which would make this a lot easier, but unfortunately we can't use it. So when it comes to these types of problems, typically your best first step is to just build some sort of equation involving the variable that you're looking for, in this case, Vx. And due to the nature of the definition of Vx, we really have only one option available to us, and that is to do a KVL. Specifically a KVL around the entire circuit here. Now we have some other options in terms of what we could do for a KVL, right? We could do something like this where we go down here, or we could do something like this where we go through there. But that's unfortunately going to require us to define some new variables. We'll need a current through this resistor, and we'll need a voltage across this current source. And those are all new things. And for the sake of simplicity, we want to try to keep variables that we introduce to the problem down to a minimum. So we're going to take this outer loop because we don't have to create any new variables to do so. So let's start with a KVL. I always like to start on the bottom left here. So first we have a 4 ohm resistor here. Now there is a trick that you can kind of apply here, and it involves this loop right here. So whenever you have a loop like this with the same current going in and the same current going out, there can be no current that travels away from the loop or towards the loop. And you can see this using a KCL, because I know that probably didn't make a lot of sense, but essentially we know that IQ is traveling in a circle like that, right? So if IQ is entering this junction, then we know IQ is leaving this junction. And let's create a new variable, call it I1, and just do a KCL here. So the currents leaving is I1 plus IQ, and the current entering is also IQ, so we'll do minus IQ equals 0. And obviously these currents cancel out, so you're left with I1 is equal to 0. So if I1 is 0, then we know that there's 0 current going through this resistor, and by Ohm's law, we know that there is 0 volts across this 4 ohm resistor. So our first term in our KVL is just going to be 0, right? 0 volts. So then we're going to continue going around, and then we'll hit this 3VQ battery. So we're going to do plus 3VQ. And then we're going to jump across this gap here because we know the voltage across it, which is plus Vx. And then plus 12 volts. And then we're going to come down here. We're going to get plus 6 IQ. And then now we're going to encounter this resistor right here, right? But we can apply the same trick that we did here to this junction right here. We know there's 0 current flowing this way, so that means this 560 Vx current source is also the current traveling through this resistor. And by definition, current enters the positive terminal of resistors. So we know the current flowing through the 5 ohm resistor is, and I will convert this to units, 0.56 Vx because it's millisiemens. So 0.56 Vx. Right? And since we're entering the negative terminal first, we'll do minus 0.56 Vx times 5 ohms. And then our last component that we're going to encounter is that battery. So it's just going to be minus 15 volts equals 0. Okay, so that's our first step. We have an equation with the variable that we are trying to solve for, and that is Vx. Now we have to look to see what other variables are in the picture and create equations for those variables as well. So we see we have VQ and also IQ. So that tells us we're going to need 2 more equations so that we can solve the system for VQ, Vx, and IQ. So let's start with IQ, just because that's going to be the easiest here. So when we're solving for currents, we have two ways to do so. The first way is Ohm's law. I is equal to the voltage across a resistor divided by that resistance. And of course, that only works if you have a current traveling through a resistor, which we do. The other method is KCL, but we don't need to worry about that because we can use Ohm's law here. And we have to bring another definition into the picture to make our lives easier, and that's going to be the fact that voltages of components in parallel are the same. So if we were to highlight our nodes here, we can very easily see that this dependent source and this 2 ohm resistor are in parallel, which means that the voltage across this 2 ohm resistor is 3 VQ. So we can use Ohm's law to say that IQ is equal to 3 VQ over 2 ohms. But here's where you have to be careful, because you remember how I said conventionally, currents enter the positive terminal of resistors. Well, here we can see that the current is entering the negative terminal of the resistor, which means that we have to include a negative sign because it's an active sign convention. You don't have to boggle yourself down in the details of sign conventions too much. Just know when you have a current traveling in the negative terminal of a resistor, you have to include that negative sign. So our second equation is just going to be IQ is equal to negative 3 VQ over 2 ohms. And then we need one last equation. And then this is where things get a little bit tricky, right, for VQ. Because we have multiple paths that we can take to solve for VQ, because we're going to need a KVL, right? It's a voltage across some gap. So that should always scream KVL. That's the only way you can really find something like that. But there's multiple paths we can take, right? We can go this way, or we can go this way. Now, the problem with the latter, the problem with going this way, is we are going to have to create a new variable for the voltage across this current source. And typically we want to avoid trying to solve for voltages across current sources because it's going to involve multiple equations to do so, and it's going to make your life difficult. It's completely possible, but it's just a more difficult approach. Now, the part that's tricky about this is that leaves one other path for us to take. However, we still are dealing with an unknown voltage right here across this 3 ohm resistor. But there's an easy way that we can solve for that. But in order to do so, we are going to have to define a new variable. Let's just call it Ix. So we have to define a new variable Ix, and I will label the corresponding polarity as such. And now let's just write out our equation for this KVL right here. It's going to be plus VQ minus 3 ohms Ix plus 6 IQ equals 0. And as we can see, we have a new variable Ix, which means now that we have a fourth variable, we're going to need a fourth equation. But there's an easy way to write out an equation for Ix. Remember how I said when you're dealing with currents, you have two ways to solve for them. That's Ohm's law and KCLs. However, Ohm's law is only going to work if we have a known voltage across this resistor, which we don't, which means we would have to define a new variable, call it VA, and then we would need a fifth equation, which is not optimal, so we don't want to do that. So that leaves us with one other option, and that's KCL. Obviously, we can't do a KCL at this junction because there's zero current entering. So you just have Ix entering, Ix leaving. That doesn't tell you anything. So that leaves you with one other junction that you can do a KCL at, which is this one right here. So let's do the KCL here. We know that we have Ix entering, so I'm going to do minus Ix. And then we also have 560 Vx leaving, or 0.56 Vx leaving. And now we have one last current here. But using the same definition I talked about with voltages in parallel, we know the voltage across this resistor is in parallel with this voltage. So it's just VQ. And we can use Ohm's law to represent that current. And let's say this current is leaving, like such. And once again, we're dealing with a current in active sign convention, a current that's entering the negative terminal. So we're going to have to include a negative, and then it's just the voltage divided by resistance. We know the voltage is VQ. We know the resistance is 7 ohms. And that's it. That's our three currents. So we just set that equal to 0. So now we have 4 equations, 4 unknowns. From here, you can plug into your calculator and be able to solve for Vx. And from there, you have to find the power delivered and power absorbed by these two sources. If you want, I can make a video going over that as well. But hopefully the information that you got from this is enough for you to turn around and solve for these values. In order to do IS1, you are going to have to define a voltage across this battery and solve for it and use the formula VA times I, which is 0.56 Vx. Right, so you're going to have to find a way to solve for this voltage, but it shouldn't be too hard given at this point you have VQ and you have Vx. So yeah, and then same with VS3 right here. You're going to have to solve for this current leaving, which is IX. You already have that at this point. So you can just do VS3 times IX to get that power. Just be careful with the wording here. It's power absorbed. And yeah, you just have to be careful with sign convention when it comes to power absorbed by sources. So let me know if you have any questions. I hope this made sense. And yeah.